Hello and welcome to another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and today we'll be doing Unit number 3, Lesson number 1, Introduction to Functions. Before we begin this very important topic and lesson, let me remind you that you can find the worksheet that goes with this video, along with a homework set, by clicking on the video's description or by visiting our webpage at www.emathinstruction.com. Also, just to remind you about those QR codes at the top right-hand portion of our worksheets, use your smartphone or a tablet, scan the code, and come right to this and other videos. Great, let's begin. Hey, there's my QR code. All right, now let's begin. The definition of a function. Almost all higher level mathematics is based on the concept of a function. So understanding its very elegant and very simple definition is important. Let's take a look. A function is a clearly defined rule that converts an input into, at most, one output. All right? Often we think about this as just being kind of like a box. All right? We got some box, represents our function. An input goes in, very often it's an x value, and a single, and this is important, a single y value comes out, all right? At most, no more than one output. The reason that we can't just say, hey, it converts an input into one output is that sometimes if you put an input in, you don't get an output out. For instance, if I asked you how many days were in the month of Illinois, you'd have to say that I was crazy, because that input doesn't even make sense, and therefore you can't give me an output. All right? But when there is an output for an input, there can be only one. Oh, now, excellent. These function rules have to be clear. All right? They must be clearly defined. And the way that they're defined often with numbers is in 4 different ways. Some people even call this the rule of 4. Very often they're defined using equations, right? Sometimes they're defined using graphs. Very often they're defined using a table of some type. And sometimes they're just defined using some kind of a verbal description. All right? So we're going to get use with all of these different forms. And in some problems, we're going to be using more than one of them. In fact, in the first problem, we're going to really put ourselves through the motion and understand functions, these rules, in all these different ways. Okay, I'm going to just clear out those little blue lines, and let's jump into the first exercise. Okay, exercise number 1. Consider the function rule. Multiply the input by 2, and then subtract 1 to get the output. All right, so let's try to understand this rule right now. Multiply the input by 2, no problem, and then subtract 1 to get the output. I think I can do that. Let's generate a table that shows a little bit of this rule being applied. Letter A says, fill in the table below for inputs and outputs. Inputs are often designated by X and outputs by Y. So what does it say? It says take the input and multiply it by 2 and then subtract 1 to get the output. So 2 times 0 is 0, minus 1 gives me negative 1. All right, so an input of 0 gives me an output of negative 1. All right, let's go with an input of 1. Right, if we have an input of 1 and we multiply it by 2, and then we subtract 1, that's pretty easy. 2 times 1 is 2. Minus 1 gives me an output of 1. Sorry, it doesn't quite look like a 1. That looks a little bit better. When my input is 2, and I multiply it by 2, and then subtract 1, I get 4 minus 1, which gives me an output of 3. And then when I multiply my input of 3 by 2 and subtract 1, I get 6 minus 1, and I get 5. All right, so that's simple enough, right? Inputs, outputs. That's it, right? And only one. Notice we only had one output for each of those given inputs. In out. Now, letter B says, write an equation that gives this rule in symbolic form. Okay, well, here we go. Here's my output. Now, how do we calculate my output? Well, in each time, what happened was we took our input. Here, I'm going to underline our inputs with this red. We took our input each time, and we multiplied it by 2. Right? We took our input, we multiplied by 2, and then we subtracted 1. So there is the symbolic rule for our function. There it is. And finally, we can also graph it. It says use your table in A to help. Okay, now we haven't done a lot of graphing, but it's pretty easy to create coordinate pairs here, right? Remember, x always comes first, so we have the coordinate pair 0, -1, the coordinate pair 1, 1, the coordinate pair 2, 3, and the coordinate pair 3, 5. Again, this is where I'm getting the x coordinates, and this is where I'm getting the y coordinates. So when we plot, right, 0, -1 is here, 1, 1 is here, 2, 3 right here, and 3, 1, 2, 3, 4, 5 is right here. We could keep going, right? If we had 4, if we wanted the output for an input of 4, just to see if we could fill it up, that would be 8 minus 1 or 7. So we'd get 4, 7, which would be right here. Right? I can actually draw that. Uh-oh. That's not the way I wanted it. Well, there's no real way of getting rid of that besides doing that. Here we go. I'll just manually draw the arrow on it. All right. And there's our rule, right, in graphical form. Of course, I'm connecting these dots because we can have inputs that are non-integers, right, that aren't whole numbers. We could have an input of 1/2, which would actually give me an output of 0. Okay. Now notice on a graph, right, and just in general, inputs are thought of as the x-coordinates, outputs are thought of as the y-coordinate, and that means for every x-coordinate there can be only one point, at most one point. You can only have one y for a given x. All right, now this was a very, very full exercise. So pause the video now, think hard about what we did, all right, and write down what you need to. All right, here we go. All cleared. Let's keep moving on. Exercise 2. In the function rule from number 1, what input would be needed to produce an output of 17? All right. Now, this is kind of cool, right? It says it's actually asking for the input that I would need to get an output of 17. Now, I'm going to write down our rule in symbolic form. It was 2x, y equals 2x minus 1, right? The verbal description was multiply the input by 2 and subtract 1 to get the output. I'd like you to pause the video right now and do some problem solving. Try to figure out what input you would need to get an output of 17. All right, well, the problem didn't specify how you had to do this. So if you played around with it with guess and check, I think that's awesome. If you tried to extend the graph that we made in the first exercise using a larger piece of graph paper to try to find a y coordinate of 17, that's great as well. I'm going to go with sort of the easiest approach that I know of, which is to take my output and make it into 17. See, then I can use algebra to find that input, right? So I know the output is 17. So I'll solve this equation by using properties of equality, right? The additive property of equality allows me to add 1 to both sides. And then the multiplicative property of equality allows me to divide both sides by 2. So we need an input of 9 to get an output of 17. Now, I think that the second question is almost as important, if not more important, than the first. It says, why is it harder to find an input when you have an output than finding an output when you have an input? Now, I know there's a lot of input, output, output, input stuff in this question, But think about it. Think about how easy it was when I gave you an input of x equals 2 to find an output of y equals, I guess it was 3. And then when I gave you an output of 17, it's actually kind of hard to find an input of 9. Why is that? Well, I'll write this down in a second, but it basically boils down to the following. All right, function rules tell us how to convert an input into an output. They do not tell us how to go in reverse. They do not tell us how to find an input if we're given an output. So function rules, and they do rule, function rules tell us how to convert an input into an output, not the other way around. Right? Now in Algebra 2, you're going to learn about things known as inverse functions. And inverse functions do that, right? They tell us how to undo what an original function has done. But for right now, we're not going to be working with inverse functions. We're just going to be going in the forward direction. To go in the backwards direction, to find the inputs if we're given outputs, will always be harder. But that's okay. We'll find ways to do it. All right, I'm going to clear out the text, so copy down what you need to. All right, here it goes. Moving on. Exercise 3. A function rule takes an input n, so that's just what we're calling it. This time it's not x, and converts it into an output y by increasing 1/2 of the input by 10. Determine the output for this rule when the input is 50, and then write an equation for the rule. All right, pause the video now and see if you can do both of these things. Start with the verbal description of the function. Try to use the verbal description to change that input of 50 into an output. And then, based on what you did to the 50, write a rule involving the y and the n. All right, let's go through it. So let's take a look. Verbal description of the function, right? That's what we're given first. What do? We're going to increasing 1/2 of the input by 10. All right, well, let's start with the 50, right? We'll go with the 50 first. So we want to find 1/2 of 50. That's easy enough. That's 25. And then we want to take the 25, and what do we want to do? We want to increase it by 10. So, in other words, right, if we think about our little function diagram, when 50 goes into our function, wouldn't it be great to have some notation for functions? What comes out is 35. Now the question is, can we do the same thing with our box, our fun function box? If we put n in, what comes out? Well, we've got to write a function rule here, and that's going to be an equation. An equation, an equation, an equation has to have an equal sign, folks. Don't forget it, okay? Now, what gives us our output? Well, we take our input and we find 1/2 of it. We could either multiply by 1/2 or divide by 2, your choice. And then we're going to increase it by 10. That doesn't even look like an n. Let me make a little bit of a better n for you. So there it is. There's our function rule in equation form. We've been given the function rule in verbal form. We translate it into an equation form. The beautiful thing about the equation form, obviously, is that it will allow us to convert very quickly various inputs into outputs, if we needed to. All right? So I'm going to clear out this text. Pause the video now if you need to. All right, here it goes. So let's keep going. We want to work with functions in as many different ways as we can. All right, and remember, at its base essence, all a function is a rule that takes an input and gives us an output. Those inputs and outputs are mostly numerical, mostly numbers, but they don't have to be. So let's take a look at one in exercise 4 that is not numerical. Function rules don't always have to be numerical in nature. They simply have to return a single output for a given input. The table below gives a rule that takes an input as an input, a neighborhood child, and gives as an output the month he or she was born in. Letter A. Why can we consider this rule a function? Notice the little typo here. We'll get rid of that eventually in the worksheets. But why can we consider this rule a function? Think about this for a moment. Pause the video if you need to. All right, let's talk about it. Well, for each child, and let me just put this in parentheses, input, there is only one birth month. And that would be output, right? I was born in December. I wasn't born in December and January, right? So if the input is the child, the output is the birth month. There is only one output for each input. Letter B is easy. What is the output when the input is Rosie? Well, simple enough, right? The output is February. All right. So, right, when Rosie goes into this function, what comes out is February. Finally, letter C says find all inputs. So here we're going in reverse. Find all inputs that give an output of May. All right. Pause the video right now and do that. And also try to answer why that does not violate the definition of function, even though there's two answers. Pause the video now and see if you can handle that. All right, let's go through it. Well, what are we looking for? We're finding all the inputs that have an output of May. Well, there's an output of May. There's an output of May. And now we're going to go backwards. And we're going to figure out that Zeke and Nico are valid inputs that give us an output of May. Now, it seems like that shouldn't be a function, and yet in letter A we said, no, this is a perfectly good function, right? The reason that we can still consider this a function is because a function does not insist that each input has a unique output, okay? Outputs can be repeated, and that's the important thing. Outputs can be repeated in functions. Inputs cannot. Inputs cannot. All right? There's no problem with an output being repeated. All right. So, let me clear out the text. Pause the video now if you need to. All right, let's go on. Let's do it. Okay, this last problem, we've got a beautiful function given by a graph. Let's take a look at what the physical scenario is. Charlene heads out to school by foot on a fine spring day. Her distance from school in blocks is given as a function of time in minutes she has been walking. This function is represented by the graph given below. Let's answer some questions. And actually, what I'd like you to do now, because you've done a lot of work in the past with just looking at and interpreting graphs, is I'd like you to pause the video, spend up to maybe even 10 minutes taking a look at this graph and the questions that are asked about it, and see if you can come up with all the answers, all right? And then we'll go through them one by one. All right, let's go through the problem. How far does Charlene start off from school? All right, well, that really gets at the idea of where was she at 0 minutes? Well, if I look up and watch out, the scale is by twos, right? That could be a little tricky if you don't look at it carefully, right? It's 2, 4, 6, 8, 10. Well, it's clear that she starts off 22 blocks. Don't forget your units. She starts off 22 blocks from school. Simple enough. Notice only one output. Letter B. What is her distance from school after she's been walking for 4 minutes? Well, here's our 4-minute input. And it appears 10, 12, 14 that she is now 14 blocks from school. She's making progress. It's a long way to walk to school, right? Depending on how you look at it, 22 blocks is, it's over a mile. But hey, it's either that or the bus, right? Letter C. After walking for 6 minutes, Charlene stops to look for her subway pass. How long does she stop for? All right. Well, here's our 6-minute time. Now, how can I tell that she's stopped, right? I can tell that she's stopped because at 6 minutes, she's 10 blocks away from school. At 7 minutes, she's 10 blocks away from school. At 8 minutes, she's 10 blocks away, etc. In fact, she remains 10 blocks away from school between 6 and 9 minutes. So for 3 minutes, right? For 3 minutes, she stopped. And that's symbolized by sort of this, this, and this. Letter D. Charlene then walks to a subway station before heading to school on the subway, a local. How many blocks did she walk to the subway? Well, let's take a look. Now, as she's riding the subway to school, right, she's going to be getting closer to school. But if you've ever been walking down a sidewalk, let's say, I don't know, in Brooklyn or something like that, and you pause, you might realize that you overshot the subway stop, right? So maybe you have to walk a little bit away from the school simply to get to the subway stop. So it's at this point, right, that she's actually traveling on the subway, right? This is when she's on the subway. So how many blocks did she walk to the subway? Well, right here she's at 10 blocks. Right here she's at 12 blocks. So she must have walked 2 blocks to the subway. Now, how long did it take her to get to school once she got on the train? Well, she must have gotten on the train at 11 minutes, and then she was at school at 15 minutes. The time that elapses between 11 minutes and 15 minutes is 4 minutes. I know this is idealized. I know students and teachers who are looking at this and they've been riding the A or the 3 or the 2 or the 9 and in New York City realize that, okay, you're probably standing on that subway platform for a while before you even get on the train. But still, that would make for one complicated graph. All right? Anyhow, I'm going to be clearing out the text, so pause the video now if you need to. Here it goes. All right, let's wrap up this lesson, shall we? So today we introduced quite possibly one of the 5 most important ideas or concepts in all of math, that of a function. A function is a rule. Doesn't have to be simple, doesn't have to be complicated, but it has to be clearly defined. A clearly defined rule that takes inputs and converts them into at most one output. One output. All right, we're going to obviously be working with functions a lot more, and in fact, this entire unit is devoted to them. So, thank you for joining me for another Common Core Algebra 1 lesson. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.